Well, welcome back. This is Unit 6.3. In our discussion on reactions, we're going to talk specifically about oxidation and reduction reactions, and this is in Chapter 19 of your textbook. All right, so in our first section of this unit, we learned about the 5 main types of chemical reactions, and in our last section on stoichiometry, we learned about a subcategory called the precipitation reactions. And there's another subcategory of reactions called oxidation reduction that we need to talk about. And in oxidation reduction reactions, elements will gain or lose electrons from the reactant side to the product side. And this is important because this gaining and losing of electrons gives off large amounts of energy, and it's this energy that's used by the cells in our body that support life. So if you'll remember back to biology last year, you may have studied the Krebs cycle or the ATP cycle, sometimes is what it's called from biology, and this is a great example. Oxidation reduction equations, for short, are usually single replacement reactions, combustion, synthesis, and decomposition reactions, while the double replacement reactions are what they call metathesis. They do not transfer electrons. Now, there are exceptions to this rule, so how can you tell the difference? Well, we have to know what's called the oxidation state of elements that are in compounds and of elements. So they're almost always the same as the charge. You know, we learned the charges of elements for ionic bonding. It's almost always the same as the charge, but you know, this is chemistry, so there are exceptions. So this table below right here provides a quick reference for you. And this is not in your reference material, so you're just gonna have to know this, sorry. So go ahead and pause the video and write this table down in your notes. All right, hint. I always assign oxidation states from right to left, so backwards of the way that you read. And this almost always encompasses all the rules. So that way I don't have to remember every single rule. Because remember, I said before, this is almost always the same as the charge. Okay, so let's look at a couple of examples. All right, so let's take H2CO3, carbonic acid. All right, so I'm going to start from right and I'm going to work backwards, right to left. So oxygen. So the oxidation state or oxidation number of oxygen is always a -2. Well, if we think about the charge of oxygen, oxygen is always a -2. So this goes along with the charge. So this is rule number 3. Okay. Now, since CO3, let me just write this separately. Carbonate, okay, is a polyatomic ion with a -2 charge. If each one of these oxygens is a -2 and we have 3 of them, that's a -6 total, right? Well, the carbonate ion overall is a -2. So whatever carbon is, we have to have a -2 left over. So what can we add to this +6 to leave a -2? Okay, so that's going to be a +4 because +4 -6 is a -2. So this has to match our charge of our polyatomic ion. So that means that carbon here is a +4. Okay, and that's rule number 6. All right, and hydrogen is always a +1 in most cases. And so that's rule number 4, unless it's a metal hydride, which means that the hydrogen is bonded to a metal. It comes second, like lithium hydride. Okay, so when we think about an ionic bond, it's always positive, negative, always positive, negative. So if I know it's positive, negative, and a hydrogen sits here in this second spot, well, I know that hydrogen now is a -1. Okay, so that's rule, I don't know, what is that, rule 4. Okay, so it's a metal hydride. That means this has to be negative because the lithium is positive. Okay. So see, if you assign them from right to left, it usually meets all the rules, 99 times out of 100. Okay. And so bonded with the hydrogen here, if this is polyatomic ion is a -2, and we have two hydrogens, each one of these hydrogens is a +1. So the hydrogen in this is going to be a +1 because of rule number 4, this whole thing has to be at 0 charge. Okay, another example, just PO4, the polyatomic ion. All right, so we're going to start with the oxygen. Okay, if oxygen in PO4 is a -2, we have 4 of those, so that's going to equal -8. Okay, now this whole thing has to be a -3 charge. So what can I add to a -8 to have a -3 left over? Okay, so that's going to be a +5. Okay, and then that way it leaves a -3, so the phosphorus must be a +5. So rule number 3, oxygen's always -2. Okay, and then phosphorus, whatever's left over, has to be a +5. Okay, so that's rule number 6. So here, normally, if you look on the periodic table, phosphorus is not a +5 charge. Phosphorus is usually, I think, a -2 or a -3. I forgot what group it's in, but it's certainly not a positive. So if we just go from right to left, then it meets the rules of oxidation states. Now, remember, it's almost always the same as the charge. So remember, the charge is not the same thing as an oxidation state. They're two separate things, but it's almost always the same as the charge. All right, one more example. FeNO3. All right, so working right to left, we're going to start with the oxygen here. The oxygen is -2. So we have 3 of them. So that's a -6. But remember, NO3 is a -1 charge overall. So what can we add to a -6 to leave a -1? That's going to be a +5. So the nitrogen here has to be a +5. Okay. Now, this NO3 is a negative charge. We have 2 of them, so that's -2. So that must mean this iron is a +2 because this compound has to equal neutral, 0. Right? So iron is a +2, rule 5. Right? So it just needs a little practice, but you can do it. So oxidation and reduction defined. The official definition of reduction is a decrease. So reduction is a decrease in the oxidation state of an element. So oxidation is going to be the increase in the oxidation state of an element. Now that's the official definition, but it's not always easy to remember oxidation reduction like that. So we're going to use an acronym, and it's an easy way to remember what's happening here. So the acronym is oil rig. So oxidation is losing oil. Reduction is gaining rig. And that's, of course, electrons. Now, another one that you might see, I don't use, but a lot of people can remember this easier for some reason, is Leo the lion says grrr. Leo the lion says grrr. Now what that means is losing electrons is oxidation. Gaining is reduction. Grrr, gaining, reduction. You can use either one you want. It doesn't matter to me. This one makes more sense to me. This one was what I was taught in high school, and this is the one that I always use. All right, doesn't matter. All right, so let's look at an example of a reaction here. So the first thing that you need to do is make sure that you have a balanced chemical reaction. Remember, I said a couple of weeks ago, from here on out, when you see a reaction, it doesn't have coefficients, balance it. If it's got coefficients, it's already balanced for you. But we must work with balanced chemical equations. All right, so manganese 1, manganese 1. Okay, I'm going to skip oxygen. I'm going to skip hydrogen, chlorine, chlorine 1, chlorine 4. I've got it in 2 different places. So I've got 4 chlorines on this side. So I need to add a 4 here to make 4 chlorines on this side. Okay, now we can do hydrogen and oxygen. There's no carbon here, so hydrogen and oxygen. So hydrogen, 4 hydrogen here, 2 here, so I need to add a 2 here to make 4 hydrogen. Okay, now oxygen, we have 2 oxygen here, none here, 2 oxygen here. All right, so that makes this a balanced chemical equation. All right, so now we're going to go through and we're going to start assigning oxidation states to each one of these elements. All right, so oxygen here is a -2. Okay, now when you assign them, we're assigning to the element. Now there's 2 oxygens there, so that really makes a -4. The only reason we use that is so we can tell what the manganese is, because remember that has to equal 0. So you may be tempted to say, well, this is a -2, but there's 2 of them, so it's -4. No, that's not correct. We're looking at the charge of a single atom of oxygen within this compound or molecule. All right, so -2. So we have 2 of those, that's -4. So that must mean that this manganese, since we only have 1 of them, is a +4. Okay. All right, chlorine, -1. So that must mean hydrogen is a +1. Okay, here, chlorine, -1. We have 2 of them, so that means that this is +2. Okay, so elements that sit by themselves, elemental, diatomic elements, or anything that sits by itself, always has an oxidation state of 0. Okay, I think that's rule number 1. So really, this is one that you had to remember. When it's by itself, it's always 0. All right, and then H2O, oxygen's -2 here. Okay, we have 2 hydrogens, so each hydrogen is a +1. All right, so we've gone through and we've signed oxidation numbers, oxidation states to each one of these elements. Now we're going to look for elements that have changed from the reactants to the products. Okay, so here we have, and I just start, left to right, just like I balance the equation or I assign the oxidation states. So I'll start looking. All right, so here's manganese. Manganese is a +4 on this side. So if I look on this side, the manganese is +2. Okay, so it's changed oxidation states. So that's 1. Now, when I have 1 that changes, always have another one that changes, always. Okay, so let me change colors here. And oxygen, -2, -2. Okay, so oxygen is not the one that changed. Hydrogen, +1, +1. So hydrogen didn't change. Chlorine, -1, -1. But we have chlorine in 2 different places. Here we have chlorine and it's 0. So chlorine did change in this case. All right, so one of these is oxidized and one of these is reduced. So I have manganese and I have oxygen. So now we need to decide which one is oxidized and which one is reduced. Well, reduction is gaining electrons. So if something gains electrons, it becomes more negative. So +4 +2. That's kind of confusing. Well, if this is a +4 and now it's a +2, in order to do that, it had to gain 2 negative charges, right? Because +4 +2, so this gained electrons to make that charge reduce. Okay, it reduced the oxidation state. Okay, so this is gaining. So I'm going to label this reduction. Okay, and it went from a +4 to a +2. Okay, now if this is gaining, that means that oxygen is losing electrons. So let's see. Here we have chlorine. I said oxygen, I'm sorry. Let me back up. That's not oxygen, it's chlorine. Okay, chlorine. All right, I apologize for that. If it confused you, I'm sorry. Okay, so chlorine. All right, so chlorine here starts off with a -1 and it goes to 0. So we have this negative charge here, but it's gone here. So that means that it is losing that 1 electron. Okay, losing electrons. Okay, so this is oxidation. Redox, red ox, reduction oxidation. So this is going from a -1 to a 0. Okay. So the chlorine is losing electrons. All right. Now, this is always the same number of electrons from right to left. Okay, so if this one gains electrons, this one is going to lose the same amount of electrons. Oxidation and reduction always happen together because remember, you cannot create or destroy matter. Electrons are matter, so when you figure out which element is oxidized, the other one is always going to be reduced. They come in pairs. Okay, so little vocabulary here. Agents. Agents are the cause of something. So one element in the reaction is causing another to gain or lose electrons. So if an element is reduced, then it's gaining electrons and then therefore is an oxidizing agent. So it's kind of the opposite. If it's reduced, it's an oxidizing agent. If it's oxidized, it's called the reducing agent. Okay, so you'll see these terms agents in your homework or on your test. So that's some vocabulary that you're going to see. So make sure that you understand and learn that. All right, and that is it for oxidation and reduction. Make sure you slap that like button right across the face. You give me a thumbs up and perhaps leave a comment.